So what's going to happen with these equations, these exponential equations, when we can't rewrite our equation with the same base value? That's almost like a cheat code in some sense, right? Because you just cancel out the whole base value and just work with the powers, and it gives you a pretty simple equation. But obviously, if I start to use things that don't have different base values, I'm going to have to use some sort of other strategy. And so what we're going to have is sort of, again, so our form here, we're going to have some sort of b to the x, equals c or something. And so our sort of general problem is if I can't just cancel the base values away, if I can't rewrite it and get the same base on both sides and just wipe it out, how the heck am I supposed to get up into the exponent? And the answer is we're going to use logs and log rules. In particular, we're going to use the natural log and log rules, in particular power rule. And so what we're going to do is take the natural log of both sides. So the nice thing about equations, right, is that I can do essentially any math that I want to both sides of the equation, provided that I'm consistent and do the same thing to both sides, right? So if I know that b raised to the x equals c, I know that sort of natural log equation is 1 to 1. So what this is going to allow me to do is take the natural log of both sides, and that keeps the whole equation equal, right? The natural log of b to the x is going to be equal to the natural log of c, where b to the x is equal to c. No big deal. The idea here is that the b values and the c values are just going to be numbers, so then that means the natural log of those values would also just be numbers. They're going to look kind of strange, right? Because they're logs of these values. But in theory, they're just some sort of decimal numbers, right? What this allows us to do then is use our power rule on the left. So this is going to be x times the natural log of b, right? I can bring my exponent down, which in theory is where my variable is, and of course this would also work if there was more action up here, if this is an x minus 2 or a 2x plus 5 or an x squared minus 6x plus 3 or something, right? All sorts of things will work. So this is just going to be x times the natural log of b equals the natural log of c, and the idea here, right, is that natural log of b is just a number, natural log of c is just a number, so I can sort of get as a final form, just by doing a little division, x would equal whatever this natural log of c value is divided by the natural log of b. So that's going to be kind of our generic form. And in some sense, I mean, not every problem is going to go with exactly those steps, but you would expect your answers to look something like this. We could have a little bit more algebra that happens, and of course if that does happen, we'll deal with that. Let's run an example with an actual sort of real setup. We'll do one that's a little bit sort of shorter first, and then we'll do a little bit of a longer one. So what do we got? I don't know. How about 7 raised to the x minus 3 equals something that obviously is not a power of 7, like 15. The numbers here are really totally random. I kind of on purpose am trying to pick numbers that aren't related to each other. I don't want a way to get 7 and 15 synced to the same base, because the whole point of this is that they're written to different base values. So there's no way to get these base values together, so we're going to do natural log of both sides. So that's going to be the natural log of 7 to the x minus 3 equals the natural log of 15. And from there, what I can do is I can bring this exponent down in front. So this is going to look like x minus 3 times the natural log of 7. So you can see, right, natural log 7 is just some number, right? It's like, what would the exponent be to get us from the base value e to 7? I I don't know, something, right? Some sort of decimal number would do the trick, but who knows what that number actually sort of is very accurately. This is sort of calculator problem stuff. To get to this x, I need to do a little bit of algebra, right? I'm going to have to do a little bit of a distribution. The trick here is you just want to sort of mentally, or maybe even not, actually. Why don't we do a division first? What I was going to say is you just need to sort of tell yourself kind of over and over again, because it doesn't look like it, that the natural log of 7 and the natural log of 15, it's just as good as having a 7 or a 15 there, right? They're just numbers, and so we're going to treat them just like numbers. We're not going to try to do anything sort of strange with them. We're just going to sort of think of them like they were 7s and 15s, and sort of just try to do the typical algebra steps to sort of get us to our answer. So in some sense, instead of doing a distribution, let's actually do a division first. If I just divide both of these sides by natural log 7, that kind of gets the natural logs just like grouped together, right? So then this would sort of get me this x minus 3 on the left equals this fraction, because the idea, right, is that these guys will cancel out. Natural log 15 over natural log 7. You're going to be extremely tempted to try to say, oh, this is like a division, right? So that would be like natural log of like 15 minus 7 or something, but it doesn't work that way, right? This is a slightly different form than all of our different log rules, so this doesn't quite fit into those log rules. It's not a quotient rule. It's just two, in theory, right, decimal numbers stacked over top of each other. To finish this, of course, right, to get to our x, all we need to do is add 3 to both sides. So what we end with is x is just going to be this sort of awkward log stack, natural log of 15 over natural log 7, and the whole thing is plus 3. So like, that's technically all numbers, so that's going to be our answer. It looks very strange. It's right, much different than like most of the types of answers we've gotten so far, but again, in theory, it's all numbers, and it's just using natural logs and using that power rule, that log rule, to help us clean this up and get something decent. Let's do another one. Let's do how about, doesn't particularly matter. Let's do 3 to the x plus 4. Let's throw another power over here. Let's do 6 to the 3x. So we won't go totally berserk. You can imagine, obviously, if you sort of start stacking powers on powers and doing all sorts of things, this can get pretty complicated pretty quickly. I don't want to spend 20 minutes doing an example. So we'll get tougher, but we won't go totally wild with it. The big difference here relative to the one we just did, right, is that I have now sort of exponential terms on each side, and I have terms, right, 3 and 6. 3 times 2 is 6, but there isn't a way to relate them as far as via a common base value, right? So there's no common base that we can do here, so we need to do the same thing that we just did, which is natural log of both sides. So we'll just sort of attach that onto here. So what's going to happen is I'm going to have this power rule for logs on both sides, and so that's going to get me a little bit more complicated term algebra-wise to deal with. So this is going to become, if I start to like bring these powers down, right, x plus 4 and then 3x are going to come down in front. So this is x plus 4, right, times this natural log of 3 is equal to, so this is 3x times the natural log of 6. And so what we need to do here, so now we kind of have a little bit less of a direct path to get to the x. Up here we kind of just had the 1x on the left hand side, and it's not so much work to just sort of clear away everything else. We have x's now kind of on both sides in a way that's maybe a little bit less obvious what we should be doing. However, again, this really is just a linear equation, right? This is just sort of x's to single powers. There's not x squareds. We're not trying to do any sort of like foiling or anything like that. We just have to kind of keep our wits about us and work through this. What we're going to do then is just remember to treat these natural log terms like numbers. And so what we're going to do is distribute. So this would look like x times the natural log of 3 plus 4 times the natural log of 3 equals, what I'm going to do here is I'm just going to shift, really just for aesthetic reasons, I'm going to call this x times 3 natural log 6. So the portions of this equation now that are numbers, right, are sort of grouped together. 3 natural log 6 is just a number. This whole term, 4 times natural log 3, is just a number. And then this is natural log 3 is also just a number. So in theory, if this was like x times 3 plus 4 equals, well, x times 3 wouldn't really be super helpful, but x times some other number, right? What we would do is group the x terms together, group the numbers on the other side, kind of factor out the coefficients, factor out the x, divide it away, and be left with 1x equals however much. So that's still going to be our strategy. So what we're going to do is just organize our terms. So in this case, let's just do x's to the left and just like numbers to the right. And when I say numbers, I mean strictly just this like number term, right? So what I'm going to do is sort of minus 3 times x times 3 natural log 6 to both sides. And then I'm also going to subtract this 4 natural log 3 to the right, getting a little bit like pinched for space. So this becomes x times natural log of 3 minus x times 3 natural log 6. And you could do some stuff, right? I mean, you could say, okay, that 3 is going to come up here, right? Would be natural log of 6 raised to the 3. I think it's like 216. If you want to, you can do that, but it's not necessary. I'm going to suggest just kind of leaving it for now, just to have one less thing to worry about. So it's going to equal for us on the left the negative version of 4 times natural log 3. This is getting just a little bit tight, but we should be able to fit our solution in this last little bit. So the idea is once I have x's here, right, this is sort of x times the natural log of 3 minus 3 times the natural log of 6. So that's equal to negative 4 natural log of 3. So if I factor that out, if I'm factoring sort of the x out, well then to get the x by itself, I just need to divide by this whole term. Just divide by everything here in the parentheses. So this really starts to look like a mess. I'm not going to lie, right? This just is messy. There's no getting around it. But again, in theory, it's all numbers. If we wanted to, we could sort of do a calculator version, and we could sort of clean this all up and turn it into just some final decimal. I have no idea what it would be, but it's possible, and certainly with a calculator or just like Excel or whatever, we could kind of make this happen. My final version, just to sort of write it as clean as possible, 4 times natural log 3, the negative, right? And then this is going to be over natural log of 3 minus 3 times the natural log of 6. Again, there's some simplification you could do with the logs over here. I'm just going to sort of call it for now. We'll sort of say that's like good enough for now. So that's the idea. These obviously go a little bit longer, right, once the base values are not in sync. But that's okay. We can work with it. That's what we got.